Okay, welcome everyone to our video on classifying chemical reactions. And in this video, we are going to look at displacement reactions. Here's our learning goals for this video. We're going to look at how to identify the form and recognize single and double displacement reactions. We are going to look at how we use the activity series to predict single displacement reactions. And then we're going to go through some specific examples of some common types of these displacement reactions. Now, one thing I want to talk about here before we get into this video, just to avoid some misconceptions, is the difference between classifying reactions on paper and in the lab. Because on paper, I'm going to be describing certain things that we're going to be looking for in the chemical equation. And those things that we're going to be looking for, and when I talk about elements switching partners in double displacement reactions and items like that, those are things that we're going to be using, some tools that we're going to be using to help identify these reactions on paper. When we get into the lab, we will talk more about what's actually going on in these chemical reactions and how it differs from what we see on paper. When we get into the lab, we'll talk more about the states that we have for these chemicals. You can see in this example I have on the screen, I've got solid copper and aqueous silver nitrate. We'll talk more about that in the lab. On paper right now, we won't worry too much about states. Here's an example of this reaction in the lab. And when we're classifying reactions and recognizing reactions in the lab and on paper, we are looking for we can be looking for very different things there. So once again, this video is really focused on identifying and classifying and predicting products of reactions on paper. Okay, let's start off with single displacement reactions. Our general equation, we have some metal X reacting with an ionic compound YZ. That's how we recognize it, a metal reacting with an ionic compound. And the products of the chemical reaction there is a displacement that we see on paper, that the metal X displaces. You can think of it as knocking the other metal out of the compound. So X knocks Y out of the compound. So we end up with a new ionic compound, which I've written as XZ there. And then we have some new metal which is produced. So this is the way we're going to think about it on paper, of a metal displacing another metal out of a compound. We'll see an example of a non-metal doing the displacing, a specific example of that, but most of the reactions we will look at will be a metal reacting with an ionic compound. Now, one thing that we will see a lot of, and more throughout the course, is that not all reactions that we can write down on paper will actually happen. And this is what we're going to look at for single displacement reactions. A single displacement reaction, as I said, we can think of as one metal displacing another metal out of a compound. This can only happen if the metal that is doing the displacing is more active than the metal that's in the compound. So a metal can only displace another metal if it is more active. Now, this list here says reactivity. It's not exactly the same thing. Activity is more correct. And here's another activity series. This is the one on the right, is one that you'll see on a lot of our evaluations and on our handout. So a few things to note here. You can Google search activity series and you'll come up with a whole bunch of different types. And they'll all be slightly different. Mostly they have the same common metals, but sometimes, as you can see here, the list on the right contains barium, the list on the left doesn't. Some are more comprehensive than others. But they all should have the same general format, in that it is a vertical list in which the most active metals are listed at the top, and they decrease in activity as you move down. So a single displacement reaction will only happen if the metal that is doing the displacing is higher up on the activity series than the other metal which is in the compound. So let's take a look at this example here that you have on your sheet and see how we put this into action. Before I go any further, note that you never have to memorize the activity series. You'll always be provided with one on any sort of evaluation. Okay, so here we have a common single displacement reaction, iron reacting with copper sulfate. So I'm going to switch over here to my whiteboard in a second and write out this reaction. Before I do that, the first thing we're going to check is once you've identified this as a single displacement reaction, we're going to check the activity series to make sure that the iron can displace the copper. So I locate my two elements here, go down from the top, there's iron, and there is copper further down. So iron is more active than copper, so that means iron can displace copper from this compound. So you check first before we proceed. So let's switch over to the whiteboard and complete this reaction. Okay, so here is our reaction. So our first step, what you should be doing is making sure you're clearly identifying the two metals. So there's iron and copper. I'm just going to put the sulfate in brackets here just to separate it. And since we know from the activity series that this reaction is going to occur, we know that iron is going to displace copper. And so copper gets bumped out of the compound, so it's going to be by itself. And then we're going to have iron bonding with sulfate. Now on paper, you don't necessarily know whether it's going to be iron 2 or iron 3. We'll talk a bit more about that in class. For right now, just to keep things simple, I'll make it iron 2. So FeSO4. So how did I know the ratios? Just a reminder of nomenclature. SO4, the sulfate ion, has a charge of 2 minus. And that makes sense with this compound because copper's here is copper 2 plus. So 2 plus, 2 minus, they bond in a 1-to-1 ratio. And as I said, we don't necessarily know whether it's going to be iron 2 or iron 3, so I'll just assume it's going to be iron 2 to make everything nice and easy. So we get FeSO4. Now, for right now, we could have equally predicted it could have been iron 3, in which case we would have had Fe2SO4 3. So the 2 came from the sulfate, the 3 came from the iron. So hopefully some of those ideas ring a bell. Once again, we will be covering nomenclature in much more detail in the future. So let's go back and look at this. So here's our reaction. So I did iron 3 right here, and there's our products. Let's look at another example right here. And this is a specific example where an active metal reacts with water. Okay, so here is another example of a single displacement reaction. And in this reaction here, it's a bit more tricky because the compound that's reacting with the metal is not an ionic compound. It's a molecule, H2O. But it turns out that group 1 metals can react directly with water molecules and displace one of the hydrogens out of the water molecule. So actually, I'm going to rewrite this equation and write the water and think of it like this. So think of it as hydrogen bonded to hydroxide, OH, there. So it's kind of as the form of an ionic compound. So if you check the activity series, you'll see that sodium is higher than hydrogen on the activity series. So sodium can displace hydrogen out. And what we end up with is sodium hydroxide plus hydrogen. And recall that hydrogen is one of those elements that when it's in its elemental form, it always exists as a diatomic molecule. It's always H2. So this is another single displacement reaction in which an active metal displaces hydrogen out of water to produce hydrogen gas and sodium hydroxide in this case, which is a base. Okay, so here we have the completed reaction. So here's something to try it yourself. Can you try to generate two examples? Can you generate two examples of single displacement reactions involving a metal displacing another metal, but one of them have one that which would work, and then have one that has the form of a single displacement reaction, a metal reacting with a ionic compound, but because of the location of those two metals on the activity series, that reaction will not actually occur. So one reaction which will work and one reaction which will not work. So let's move on to double displacement reactions. So in double displacement reactions, we have reactions in which we have two ionic compounds reacting together. Almost always they are in solution, they're aqueous. Those ionic compounds could be acids. They act like ionic compounds where the hydrogen acts as the cation or the metal in the reaction. And so if we look at the general equation on the reactant side, we see two ionic compounds. On the product side, we see two ionic compounds. And we see that the pairs, the metal, non-metal, or cation, anion pairs have switched partners. Okay, so the ions have switched partners in the reaction. So let's look at some examples. So here we have two ionic compounds reacting together. So it has the form of a double displacement reaction. So an ionic compound is a positive and negative ions bonded together. Sometimes those ions just might be two elements like sodium chloride. But sometimes the ions is a group of elements like NO3 nitrate, which are bonded together with a metal. So our first step here is to identify each ion. And then we're going to figure out the charge on each ion and then make the products. So here's what I've done in the second step. I've color-coded and put brackets around each individual ion that makes up each ionic compound. The metals or the cations in red, the anions in blue. So recall that that 3 beside the oxygen belongs to the NO3 group. That's all one group. It's a polyatomic ion which works together. So I've identified the ions. Sodium's in group 1. Chloride is in group 17, always has a 1 minus charge. So and we can see they're in a 1-to-1 ratio. So when I reverse the crisscross, I see, yep, that makes sense. Sodium has a 1 plus charge. Chlorine has the chloride ion has a 1 minus charge. Silver has a 1 plus charge. It's in a 1-to-1 ratio with the nitrate group. So we can see that the nitrate must have a 1 minus charge. So that entire group, NO3, all has a 1 minus charge together. They move together. And now we'll just switch partners. Sodium bonding with nitrate, 1 plus 1 minus, they bond in a 1-to-1 ratio. Silver bonding with chloride, 1 plus 1 minus, they bond in a 1-to-1 ratio. So here I'm reversing the nomenclature to figure out the charges, and then we use those charges to properly write the ions. Let's look at one more example here. And try this one yourself, okay? So here we have two ionic compounds, potassium iodide, reacting with lead to nitrate. So can you identify the two ions? Can you identify the charges on each of the ions and then switch partners, and can you bond them in the correct ratio? So maybe pause the video right now, and before I move on, try that yourself and then see if you can get the correct answer. Okay, welcome back. So let's take a look here at the answer. So just because we're starting out the year here, don't worry too much about the nomenclature. If you messed up, maybe you wrote PBI rather than PBI2, okay? Don't worry about that too much right now. And we'll work on the nomenclature as we move through the year. But the most important thing with double displacement reactions for right now, as we're learning them, 2 ionic compounds, switching partners, and so we end up with 2 new ionic compounds. One type of special double displacement reaction are acid-base neutralization reactions, where an acid reacts with a base. We'll see these a lot, and we'll talk about them in a lot more detail in the second part of the year. For right now, we recognize the acid by seeing some number of hydrogens bonded to a nonmetal or a group of nonmetals. We recognize the base by a metal bonded to the OH, some number of hydroxides. So OH, that's hydroxide. So here, in this case, the 2 metal ions are the H and the Na. So a lot of people ask, okay, why is hydrogen in group 1 there with all those other metals when it's a gas? Well, it's because in a lot of reactions, when hydrogen is in a compound, hydrogen is acting like a metal. It has this, it's a positively charged ion. Our 2 non-metal ions are the chloride ion, Cl1- and OH1-. So we switch partners and we end with NaCl and HOH, which is just always written as H2O. So a neutralization reaction, a double displacement reaction between an acid and a base, and the products are commonly said water and a salt, but specifically, we're going to get water and then an ionic compound that is formed between the metal that was in the base and the non-metal, or the cation, or the anion, which was in the acid there. So a specific type of double displacement reactions. Okay, so that finishes up our introduction to recognizing single and double displacement reactions on paper.